evening, everyone. Welcome to the live session on design of steel structures. My name is Saurav Kumar Singh and I am doing PhD from IIT Kharagpur. Now, coming to the previous year's assignments questions. So, here in question number 1, it has been asked that determine the plastic section modulus. So what they are asking? They are asking to calculate the plastic section modulus of ISMB 450. Okay, so this is I section. So its relevant properties are given here. D is equal to 450, PF is equal to 150 mm. Shivam. Hello.
Hello, sir. Your voice is very low.
Now my voice is okay.
Yes, sir.
Actually, I was suffering from fever, so I am having some weakness. So that is why.
Okay, sir.
So, are you able to see my screen?
Yes, sir.
Okay. See, because of my ill health, I was seeing there one of the question on discussion forum was there. So I have left it out for my week 12 live session. As my health was not good, so in this live session I will be covering previous year assignments questions. Okay, so it will be better if you will open your notebook and we will solve it simultaneously. And please don't forget to bring your calculator.
Yes, sir.
Okay, so do you have or can we proceed?
Just 1 minute, sir.
Yes, sure.
Yes, sir. Yes, sir.
Okay, so in previous year's assignment questions, first question was determine the plastic section modulus. So they are asking this plastic section modulus of ISMB 450 at the rate 72.4 kg per meter about the strong and weak axis respectively. Neglect the fillet. Okay, so uh, it is already given here, but I would request you to please verify these data which have been given here. So if you are having a PDF or hard copy of code book, then you can open it and or a steel table and you can match that these datas are correct according to the given section or there is some mistake.
Sir, why we need to just check it up?
uh, no, actually I want my learners to able to see the code book. Okay, so that is why this is a live session. So I want you to you can cross verify these things that are you able to find out these in code books or not.
Okay, sir. ISMB
450
450
and
at the
its
rate.
weight is 72.4 kg per meter.
Yes, sir. So D is yes, 450. PF is breadth of the flanges 150. Yes. Yeah. The means the data is resembling in
Okay,
the
okay,
code.
okay, fine. So now we will move further. So you have to calculate the plastic section modulus. Okay, so I will
Yes, sir.
just share sir slide in which it will be better for you to see this hint. So have you written this question, means the dimensions which are required, so have you written it?
No, actually, I have not written it up. I
Please
have to
write
write
it
it up.
down. Means relevant properties, just write relevant properties of ISMB 450.
Yes, sir.
Okay, so now let us see this slide. So how we calculate plastic section modulus? In order to calculate the plastic section modulus of a given section, we have to first of all find out the area of each and every part, and let us see, this is I section. Okay, so this axis, this is the equal area axis, means this axis is dividing this entire section into two equal halves, means your uh, centroidal axis will pass through this axis. Okay, so at this point our centroid is here, so it has been shown here by this dot. So in question, it has been asked to calculate the plastic section modulus about both the axes, means a strong as well as weak axis. So for the first time you have to calculate plastic section modulus along this axis, and in you have to calculate along this side. Okay, so in order to calculate it, first of all what you have to do, you have to calculate area of each part separately. Means first of all you will be calculating area of this part, and let us assume that it's a centroid of this area, this upper rectangular part is at this black dot. Okay, so you have to take moment of this area about the centroidal axis of this entire section. So this is the axis, means centroidal axis. So you have, when you are going to, when you will have calculated area of this section, so you have to multiply it with the distance, means distance from this point to this point. Likewise you will do for this area, for this area, and for this area. So please do it and report the answer. And I have left it
Yes, sir.
open, this figure, for your reference.
Sir, can I just tell the formula?
Yes, please.
It's breadth of the flange into the thickness of the flange, minus d by tf, plus tw, uh, d by 2 minus tf whole square. Uh, is it given? Yeah.
Match with this part. I am having some doubt in this part, second part.
Yeah. Actually, LCM has been taken here, so
Okay,
that's why
okay.
it
So
is
you have
coming like this.
simplified it. Okay, okay. So put values and report the answer.
Yes, sir.
Okay, so for the time being, when you are calculating this answer, I will be explaining this formula to remaining students who will after this live session, who will see this video. Okay, so here what has been done. So you can see in this figure. So this is flange width BF, which is denoted by BF. This is the flange width. Okay, and this thickness of this flange is denoted by TF. Okay, so here you can see that BF into TF. So this is the area of our first rectangle. So this is the, let us suppose this is the upper rectangle. So area of this rectangle is BF into TF. multiplied by distance. Okay, so what is the distance from centroid of this upper rectangle is at this point, and centroid of this entire I section will lie at this point, somewhere here. So we have to calculate this distance. Okay, so this distance they have calculated like, so what will be its distance? So total depth means total depth of this I section has been denoted by capital D. Okay, so here in this figure it has been denoted from a small h, but let us assume it is equal to capital D. Okay, so this entire depth is capital D. Now what we have to do, in from capital D we want it up to the half. Okay, so half means D by 2. So when D by 2 distance is equal to from this point to this point, this point to this point, this distance is D by 2. Okay, so D by 2 minus half of the thickness of this flange. Okay, so what is the half of the thickness of this flange? Means from this distance to this distance we have to subtract this distance, then only we will be able to get the distance of this centroid to this centroid. Okay, so this is TF, so this distance, this upper distance will be TF by 2. So D by 2 minus TF by 2. Okay, so when you are going to take the LCM, so it will be D minus TF upon 2. Okay, and from where this 2 is coming in the multiplication, this 2 is coming because in this figure we are having one rectangle, means one upper rectangle and one lower rectangle. So there are two rectangles situated at equal distance from this centroidal axis. So that is why we are again and again not calculating and directly multiplying it by 2. So we have multiplied it here by 2. Now we are left with this rectangle, means this vertical rectangle. Okay, so again we have divided this vertical rectangle into equal halves, means this rectangle and this rectangle. Okay, so what has been done here, thickness of web. So this is our web portion, so thickness of web TW, this is the thickness of web. In here it has been denoted TW, thickness of web. So this TW into this height, we want this height. Okay, so what will be this height? So this height will be D by 2 minus TF. How D by 2 minus TF? When you are going to do D by 2, total is depth is D, and D by 2 is distance of this upper point to this centroidal axis, this is D by 2 minus this thickness of flange. So we are remaining with this length. Okay, so TW into D minus D by 2 minus TF. So that has been done here. So this complete makes the area of that upper vertical rectangle into distance. So what distance we want? So centroid of this rectangle, this vertical rectangle is located at this point. Okay, so we want this distance, means distance of this vertical centroid to overall centroid of this entire section. Okay, so this distance is equal to D by 2 minus TF, thickness of flange, and half of this distance is upon 2. Okay, so that has been written here. So here they have taken H, but here we are in formula they have taken D. So that is why H has been replaced by D. So D by 2 minus TF upon 2. So that has been written here, D by 2 minus TF upon 2. And there are two vertical rectangles, one is this one and another is this one. So that is why multiplied by 2. Now when you are going to simplify it, so you will reach to this formula. Okay, so this entire formula will dissolve to this formula. So I guess Shivam has been yet Shivam has calculated that value, and so have you calculated the value, Shivam?
Yes, sir.
So what is the value?
Yes, sir. It is 1534 point 204, uh, and another is 204.99 922.
Okay, so
A answer.
answer A is correct. Okay,
Sir, I have a question. Means
yes.
week 10th, week 10th lectures. question related to that.
Week 10th lecture. So, have you put those questions in discussion
Means
forum?
where there was strength calculation for the beams. Hello,
Hello?
I'm not getting your voice.
Hello?
Hello, yes sir. Yes sir.
Now my voice is audible.
Yes, yes sir.
So, have you put that
Can I
question?
ask sir?
Have you put that question on the discussion forum?
Actually, it was related to one of the questions in the discussion forum, but I have I have another still another doubt related to that.
Okay, so you can share if I will be able to clear it right now, then I will clear it, or otherwise in my week 12 live session, I will definitely clear it.
Yes, sir. The question is actually related to the 1 minute. I have to check it up.
Okay,
We were calculating the in the web buckling strength. In the video of the web buckling strength, uh, we had the formula B plus 2 N1 into thickness of the web into FCD. For the calculation of the FCD, we require the slenderness ratio,
okay.
and that slenderness ratio was given with the effective length as 0.7 upon radius of gyration.
Can you
So,
share your doubt on this screen?
sir, actually, I can tell you the lecture page in which it was. Can you just open
Lecture
up the
number,
lecture
can
material?
you tell me the lecture number?
It was 47th.
47, okay. Yes, please see.
Yes, sir. In this, just move ahead, please. Uh, in the web buckling portion, hello.
Yes, yes. Hello.
In the web buckling portion, yes,
Yes,
sir.
this is
In the
web
web buckling
buckling.
portion, uh, please another slide. Yes, sir. One another. Yeah, this one, sir.
Yes.
Backward, please back. Where there was formula for web buckling. Yeah, this one. Sir, here, while calculating the FCD, uh, we have to check, go for the slenderness ratio for the transverse section. Means, while, are you getting what I'm trying to say?
No, till now I have not. I am not getting.
Means, when we are looking into the deflection of the column, then we have to look into the slenderness ratio of the transverse section.
Slenderness ratio of the transverse section
Means, while
means
bending, let us
uh,
think of the bending
see,
moment equation in.
slenderness ratio is equal to length upon minimum radius of gyration. Okay,
Yes,
so
yes sir.
length is whatever the length of the column, and minimum radius of gyration we find out by along which axis. First of all, we see that along which axis moment of inertia is minimum. So about that axis it
Sir,
will buckle.
sir, one thing, actually, while calculating, we don't see the length of the column, we see the lateral dimensions while calculating the uh,
Where
slenderness ratio.
which slide you are saying? See, in this slide also, the slenderness ratio, formula of slenderness ratio, lambda is equal to LE upon RY, okay?
Yes,
And
sir.
this LE is the length of the member, means longitudinal length
Uh-huh,
you have to
this.
consider to calculate the slenderness ratio.
Yes, sir. Yes, sir. Yes, you are right. Here, you are right. Uh, uh, actually, the radius of gyration. Sorry, sir. The radius of
Ha
gyration
ha.
is y upon a. So, this is for the this radius of gyration is for the lateral section. Sorry,
Okay.
this was
Ha,
my.
yes, yes, yes. Okay.
So this lateral dimension here, they here sir has used not the lateral dimension, but the for the effect, means for the length of the column, length of the web he has used, means
For, which
iy is for the web of the column.
IY, you are talking about this I section. So I is related to lateral dimension only. So moment of
In
inertia about y axis into a bt cube, what section is has been taken here?
Actually, in the in the numerical questions, then we see that instead of using this one, he is using the 1 minute.
In which lecture number? Can you please tell me?
In lecture number 49th,
49. Okay, let me open it.
when we are calculating r minimum.
See here and tell me in which slide.
R minimum, it's, yeah, here.
Okay. So,
So r minimum is I upon a. So here, TW cube upon 12. Now this is for the lateral section. Lateral section dimensions, means lateral section.
yes, 7 area effective area of web has been calculated here at 740 and btw cube upon 12. Okay, so it is also related to lateral only because this b is the width of the cross section and tw is the thickness of the web. So longitudinal
B is
direction.
the bearing length. B equals to 100 mm on the in the above lines. You can
Hi,
see.
yes, yes.
This is in the I section. When we see B is at the mid depth, B is equals to 100 plus the what to say, n means angle of dispersion length related to that.
Yes, yes.
So this is for the lateral. These are the lateral dimensions, not the means not for
Longitudinal
the.
direction means not along
Yes.
the length. So this is fine na, because uh, when we are going to calculate the radius of gyration, so radius of gyration, while calculating the radius of gyration we are interested, we have to think about which axis we are going to calculate it. Okay, when you are determined that along this axis we have to calculate it, then you have to check that means let me draw one figure here.
In the I section, you can draw.
So it will something look like this, okay?
Yes, sir. Yes, sir.
This I section.
Yes, sir. The web
So
buckling. Yes,
see,
sir.
this is its longitudinal, okay, and these dimensions, this dimension or this dimension, these dimensions are its lateral dimensions, okay. So along its longitudinal axis we are not considering its buckling. So see, buckling is in its transverse plane, okay. So this is the transverse plane, this is the transverse plane, okay. So we have to consider the buckling about, means when you are going to consider web buckling, so you have to consider buckling about means along this axis or this axis. You have to find out radius of gyration about which axis it will come minimum, okay. Along this axis, see, along this axis you can apply torsion, along this axis you can apply torsion, okay. But its web buckling or flange buckling will happen along its transverse plane. So that is why when we are going to calculate the value of radius of gyration, so we are interested in calculating the value along, either along this axis or along this axis, okay. We are not calculating about this axis, this longitudinal axis. See, along its longitudinal direction, let us suppose there is a rail on which rail has been lying and on which trains are moving, okay. So wheels of the trains are moving, so that longitudinal direction is quite long, okay. So it cannot happen that this portion about this axis, let us suppose from here, okay. If you are talking along this direction, so from there if any wind will come or any earthquake will come, so it cannot happen that this position it can buckle about like this, okay. So it will move and it will rotate about this axis, okay. So it cannot possible, it is not possible, because along its longitudinal direction its length is quite long, okay. So it cannot distort or buckle about this axis. So the probability of its buckling is about this axis or this axis. So that is why we are considering this transverse axis. So that is why while solving we are considering b or thickness of web or thickness of flange we are considering. We are not considering its longitudinal direction. So area also, area I upon a, you are calculating now from here where it has been, huh, here that formula was given, huh. So here's slenderness ratio. So this slenderness ratio, is my voice audible? Hello?
Yes, sir. Yes, sir.
Yes. So see, what is the slenderness ratio? So slenderness ratio is L upon Ry. See, what will happen? Try to understand the mechanism of the problem. What will happen? If let us suppose you are going to fix its cross section, so its cross section is not changing, okay, and you are increasing length of this member, okay, you are increasing. A time will come, okay, when it will start acting like a wire. If its length will be too long then compared to its cross sectional dimension, okay, so then what will happen, it will behave like a wire. Same case happens in the case of wire, na, means what happens if you are going to consider a means a pipe of having circular cross section. So when you are going to fix its circular dimensions, means what is the area of the cross section of the pipe, you are going to fix it. Okay, and now start increasing its length. Okay, so after one time you will increase its length and going on, and after one time what will happen, it will start acting like a wire. Means wire, because of its self weight, it will sag. What happens in wire? Because of its self weight, it will sag. Okay, so
Yes, sir.
same thing will happen in this also. So that is why we don't want our member. And see, when you are going to increase its length, now when you are going to, means if you have did practical experiments in your lab, then in column we do some experiments in which what we do, let us suppose this is a column. Okay, so what we do, we apply some load from here. Okay, and we see, let us suppose at the value of uh, 20 kilonewton. Okay, so this column will buckle. So we have some arrangements in our lab when we are going to perform the test, buckling test. So let us suppose at the value of 20 kilonewton, your this column will buckle. But when you are going to increase its length, then what will happen, it can reduce to 15 kilonewton, let us say. Okay, so now in 15 kilonewton it will start buckling. And if you are going to give a little bit horizontal force along transverse direction, then what will happen, even on a very small amount of load, say 8 kilonewton or 7 kilonewton, it will, because you have given some horizontal load, you are applying some horizontal transverse load in along this direction. So these means buckling depends on various properties. Means so that is why it is very much necessary to check the slenderness ratio, or to limit the value of the slenderness ratio, so that we can prevent its buckling. So that is the case. While the slenderness ratio, we have to check the longitudinal length, means this length. Okay, and going for the radius of the addition, let us suppose in second example, let us suppose you are going to fix its longitudinal dimension. Let us suppose you have fixed it to say 50 centimeter, you have fixed it to 50 centimeter, and now you are start and in 50 centimeter length, and let us suppose any cross sectional area you have chosen, in that column is not buckling. Now start 1 minute, 1 minute. Hello, hello,
Yes, sir.
hello.
Yes, sir. Hello, sir.
हाँ हेलो, निखिल बोलो.
Yes, sir. Can you hear me?
हेलो.
Yes, sir. Hello. Hello. Hello.
हेलो.
Hello, sir. Can you hear
हाँ
me?
हाँ, यस यस. हाँ शिव.
Yes, sir.
हाँ, so now see here. So what will happen here, when you are let us suppose you have fixed the length of your beam. Okay, now you just start reducing its cross sectional area. Okay, so at one time what will happen, in its weaker plane it will buckle, your beam will buckle initially with this cross section and this much of length, it was not buckling. But now later on, when you are fixing its length and you are just reducing its cross sectional area, means dimension of this, means you are reducing this flange thickness, or you are reducing this its web thickness. So at a time what will happen, so at the same load this section will buckle. Why it will buckle? Because slenderness ratio will is depends on its length and its cross sectional dimension. So that is why it will start buckle. Okay, So you can do this experiment with by taking various types of a scale. You at one time you can take a small scale and try to give some load over it and see that it is buckling or not. On later case, take long scale and put same amount of load on that. You can observe that with when scale length is increasing, then what will happen? Your scale will buckle at the same load and having the same cross sectional area. So you can also see with uh, this formula. So radius of gyration, so what is, when you are going to increase L, so cylinderness ratio will increase, and when you are going to increase radius of gyration, then what will happen? Your cylinderness ratio will decrease. Okay, so likewise, means wire is what we call wires are cylinder members. Okay, so why wires are cylinder members? Because its longitudinal length are quite high than compared to its lateral dimensions. So when you are increasing this thing, means length of the wire, then its cylinderness ratio will also increase and it will buckle easily. And when radius of gyration you are increasing, then what will happen? Your cylinderness ratio will decrease. So for the sections whose radius of gyration is more, then chances of buckling will be less. So that is why radius of gyration depends on lateral dimensions. Okay,
Sir, but how it is related to web buckling? I'm not getting
because
why
your
it is
web is
related.
lateral dimension na. Here you can in this picture, this entire thing, this entire cross section, means this I section what you are seeing here. So this entire I section is your what you can say, this is lateral dimension, this length is lateral, this depth is lateral dimension. Only this the length along this direction is its longitudinal length. Okay, so
Yes,
your
sir.
web is also coming in lateral dimension. So either it can buckle along this plane,
Yeah.
means what will happen? It will try to rotate like this, or it can buckle in this plane. So while this, so what will happen? So it will buckle like this, it will rotate like this. Okay, and along this axis it will rotate like this. Okay,
Yes, sir.
so this can happen, but this length is quite large, so it cannot rotate about this axis, it cannot rotate about this axis. Okay,
Yes, sir.
okay, so this is the case.
Uh,
Yes, say.
uh, Sir, but in the numerical, the dimensions are for the means longitudinal part, means
Where
bearing length. The next numerical slide that I had told you.
this one.
One. This B is for the bearing length. Uh,
This bearing length, this 100 mm, 100 mm, what only 10 centimeter. 10, even your scale is coming off means 15 centimeter scale, means length of the scale is 15 centimeter. So this is not your longitudinal length, this is your transverse length, this is bearing length 10 centimeter. You can assume that have you seen any beam of having length of 10 centimeter in practical? It is not possible na, 10 centimeter beam. So
yes, sir.
these dimensions are your lateral dimensions, means bearing length whatever you are getting na, it is written here length, but these dimensions are your lateral lengths, not longitudinal lengths.
Yes, sir.
Okay, so don't get confused. Units, see these units. This is mm. So when you are going to convert it, it is just 10 centimeter, quite small. So these are
Yes,
your
sir.
lateral dimensions. So remember one thing, that whenever you get confusion, so always remember on a layman term, you can assume like that. Let us suppose you are having provided with a rectangular column. Okay, and you are seeing that after applying some load, it is getting buckled. Okay, so your column is getting buckling. Okay, it deflects. So let uh, this is your column. So after applying some load, what happens? So this is the length of your column. Okay, length. No, I'm not talking about lateral length. This is longitudinal length of the column. Okay, so what will happen when load will come? You are seeing that it is buckling like this. Okay, so what will come in your mind? In order to prevent this buckling, what you will do? You will increase cross section of your column. You will increase its width and depth. Okay, so you will be, what you are going to do? You will increase this length, or you are going to increase this length. Okay, so by increasing these two lengths, your buckling problem will be, it is possible that your buckling problem will be short out. Okay, so are you understanding what I am saying?
Yes, sir.
So
Yes, sir.
I am talking in just layman's language, without any calculation. So when you are applying any load on this column, this is the length of the height of the column. So if it is buckling like this, then what you will do? You will increase its width, or this thickness you are going to increase. And after increasing these two things, you can see that now your column is not buckling. So what will happen when you are going to increase these two things? Its moment of inertia is going to increase. Okay, so its radius of gyration is going to increase, and when your radius of gyration is going to increase, then what will happen? Then here, when you are going to can I write here? No, I cannot write here. Okay, so when you are going to increase this radius of gyration, then what will happen? Its slenderness value will decrease, because they are inversely proportional to each other. They are not directly proportional, they are inversely proportional. So when you are going to increase one thing, then another thing will be reduced. Okay, but when you are going to increase its length, means, suppose, again going to the same thing, in let us suppose, of increasing its lateral dimension, you are increasing its length of this column you are increasing. Then what will happen? Even on lesser load, it will again buckle. For this time it is buckling on 20 kilonewton, but instead of increasing its lateral dimension, if you are increasing its height of the column, then it may be possible that it will now buckle on 15 kilonewton of load. Okay, so is directly proportional to slenderness ratio. When length will increase, slenderness ratio will also increase. Okay, and buckling will be dominated. So that is
Yes.
why slenderness ratio is length upon minimum radius of gyration. And why we are taking minimum radius of gyration? Because along which axis, if radius of gyration is less, then along that axis only it will first buckle. Let us suppose along x-axis radius of gyration is 100, and along y-axis your radius of gyration is 80. Then before reaching that 100 value, means 80 is lesser value, so it will buckle about your y axis, not about x axis, because x axis has more radius of gyration than compared to y axis. So it will buckle about y axis. So this is the case.
Yes, sir. Yes, sir.
Now coming to the second question. So here, calculate the trial plastic section for the given bending moment data. Moment is given 45 kilonewton meter. Okay, and you have to calculate the trial plastic section for this given bending moment. To account for lateral torsional buckling, you have to also take into account this lateral torsional buckling. And for this, they are saying that assume ZP, means whatever plastic section modulus you are obtaining, means by when you are going to calculate plastic section modulus using this bending moment, means this moment value. So you have to increase that plastic section modulus value by 40%. Why we are taking this 40%? Because we have to take into account for lateral torsional buckling also. So I guess this value varies from 40 to 50% or 40 to 60%. I don't remember exact value, but between 40 to 50 or 40 to 60% it varies. Okay, so here in the question itself, they have given that you have to increase this plastic section modulus value from 40%. Why they are restricting you? Because if it has been means allocated to you directly, then each and every student will calculate this value according to their assumptions. Means someone will assume 40%, someone will assume 45%, or someone will assume 50%. So answer will differ, and this is objective type question, so that is why they have restricted and given you the value of 40%. Okay, so whatever value of means plastic section modulus you will obtain, so just multiply it by 1.4 in order to account for lateral torsional buckling. So please calculate this value.
Sir, can you show the solution?
Yes, see here, trial plastic section for means you have to calculate the trial plastic section. Okay, so for the case of trial plastic section, what we are going to do, moment into m upon gamma m naught upon fy, and moment value is given in the question 1.1 and fy is 250. So we are getting value of 198 into 10 to the power 3 mm cube. So now we have to increase it by 40%. So 1.4 multiplication we are doing, so 277.2 into 10 to the power 3. So this is the trial plastic section value. So now when you are going to consider any section, so you have to take that section whose section modulus will be slightly higher than this value, not much more higher than this value. Why? Because it will make your design uneconomical. Okay, so that is why little bit higher than this value you have to take. So
Yes, sir.
what is the value? 277.2. So 277.2, these all three values are less than 277.2, and only option D is having ZP value more than 277.2. So option D is correct.
Sir, sir,
Yes,
can you tell that from where this formula in the lecture 50 has been derived? Means MCR is equal to elastic lateral buckling moment. This formula has been given
1 minute,
under
1 minute.
root
Slide number, sorry, lecture number
lecture number 50.
50. Okay,
Yes, sir. This formula MCR
no, I don't know about this formula.
is this related to structural means structural analysis or something or strength of materials?
See, shear modulus, it is also taking into account pi square ei. Uh, Euler's buckling, what is the formula of Euler's buckling column? Square ei
Sir, it
upon
is
L effective square, pi square ei
P is
upon,
equals to yes, sir.
pi square ei
Pi
upon L
square.
effective square.
Yes, sir.
Okay, and pi square. So that is pi square ei upon L square, that is equal to the means critical load, means the buckling load which we are calculating na. But
Yes, sir.
here it is calculating moment. So let us suppose this is load into some distance is equal to moment. So pi square ei llt, llt, this is also again loading part plus git. So moment of inertia 4, and GCR modulus square. So, per meter square and meter power 4 Newton meter square. No, its derivation part I am not getting, because in our curriculum its derivation part was not covered. So that is why I have not encountered this thing till now.
Okay, sir. Sir, can you just
But
means tell from where we can find this?
see, you have to check, first of all, go through Subramaniam's book, okay? And if this formula has been given there, then they might have cited the research paper from where it has been taken by the IS code book, okay? So by reading that research paper, you can get that how this formula has been derived,
Okay, sir. Thank you, sir.
okay? So, next question. For biaxial moment of channel and I sections, the interaction formula is given by. Okay. So for biaxial moment, you have to see. So diet value. This is maximum bending moment about UU axis. MU is equal to maximum bending moment about UU axis, and MDU is design bending moment about UU axis. So MU upon MDU, you have to see, plus MB upon MDV, and interaction formula is less than or equal to 1. It should not be greater than or equal to 1. Means we in interaction formula we restrict the value from 1, so that is equal to less than or equal to 1. So it has been also given in the code book. So option D is correct, mu upon mdu plus mv upon mdv, and this is for biaxial moment, means moment is coming along both the axis. So you have to check from this formula. So option D will be correct.
Sir, further videos I haven't seen, so I cannot tell the answers.
Okay, okay,
Uh,
no problem.
Sir, can you tell one thing that after this series means course, we have design of steel structures too as well. Means it is not in the NPTL, but it is there. Uh, Means
Design
I'm
of
saying
steel structures too, in
y-
uh, that what things has been covered syllabus, means what is, can you give me brief description about its syllabus?
I think it covers about the construction of warehouses. Those things means against wind load design. Those things, uh, connections part, all those things, or the means bridges, something like that. Means on which people walk, railway bridges.
Okay, so means practical implementation of this steel structure has been done there.
Yes, yes, sir. So, sir, I wanted to ask in the structure part, means you have done structural engineering. So, in that as well, there is steel structures.
No, no, no. In our MTech curriculum, we don't have means steel structures too like that, because see, in India, whatever syllabus is made na, steel structures means you can see very limited structures which are made up of steel. Okay, and rest of the structures, means majority of the structures is of the RCC. So when you are going to go for the master's course, and you are opting structural engineering as your means specialization, then you will be focusing on higher things of this RCC structures, means
Okay, sir.
reinforced concrete structures you have to focus. This means steel too, what you are talking. So type of courses or means is actually done by more specific means specifically you can say means people who are from the industries, means who are doing designing in steel firms, or if they are doing means related to railway job, if they have studied railway engineering, then they might be studying those things, because railway engineering is also a means branch of civil engineering, means you can do a specialization, means masters in railway engineering. So I think in those streams you will you can um, think that you can study these steel structures part 2.
Yes, sir. Okay, sir. Isn't it covered in the optional part of the curriculum of structural engineering?
Optional, see, in IITs courses are running, okay, not from your particular branch. If you are interested in doing, say, any coding part, also you want to learn Java, then also you can opt for any Java course in your college, and you can do its means whatever thing you want to do. If you want it as a grading course, then you can do it as a grading course. If you want to do it as a non-grading course, just want to learn the things, so you can only learn those things. So like that plenty of courses are available as optional subjects. So if you are interested, then you can opt
Okay,
along
sir.
with your means. If you are doing let us suppose you are doing your masters in structural engineering, and you are interested to study any of the subject which is not in your curriculum, and if and you can manage all subjects together, then it is up to you, you can opt for those.
Yes, sir. Okay, sir. Sir,
Okay.
in the PDF format, actually, I have seen DSS2 in the PDF format
Okay.
uh, on the NPTL. Uh, that's why I was asking that advanced steel structure or DSS2 is covered in the structural part or not. That's why I was asking.
Yes, yes. See, web lecture means the web part which you are thinking now, means you can expect in some years any professor from any IITs can make his or her video, and can publish it on the NPTEL forum. So you can expect it, but for this time being you have to if you want to learn, then you have to follow that PDF only, because see in steel structures also you cannot find much options. You have to you have only option from IIT Kharagpur, means this syllabus. If you are opting for this design of steel structures entire syllabus, then only this course is offered by on NPTEL from IIT Kharagpur only, from not any other IIT has been posted any video. But it might be possible that in coming year, or 2 year or 3 year or 4 year, you can see some of the videos also from any other IITs. Okay. So these
Yes,
type of
sir.
future related things we cannot means directly say, we can just expect, but our study cannot be means we cannot stop our study in waiting for those things na. When it will come, and if you will be interested, then you can do at that time. But from that time being, for in order to prepare for your competitions, see that whatever things is in your syllabus, and try to grasp those things from different domains. If you are not getting on it the NPTEL, then you can also follow some of the YouTube lectures if you are getting.
Yes, sir.
Okay. So let us wrap this today's live session, as means you have not seen these things, and time is also over. So let us wrap this live today's live session, and uh,
Yes, sir. Thank you,
next
sir.
live session, whatever means practical doubts so related to your career or something if you are facing, then you can also share those things, because last class will be our, means next live session will be our last class, so you can ask those things also.
Yes, sir. Thank you, sir, for telling.
Okay,
Thank you.
thank you Shivam for listening the lecture. Okay, thank you.